presentation asking the question, how do marine heat waves affect cold water corals in the deep sea? I'm an independent marine researcher based in London and have a PhD from NUI Galway and an alumni from University College London and University of Southampton. You may have followed my work on the Seabed Habitats blog, which is a science communication website at seabedhabitats.org. So just a quick introduction to the marine heat waves, the key definitions and categories. Marine heat waves are prolonged extreme oceanic warm water events of more than 5 days duration. Based on the work of Hobday et al., who defined marine heat waves in the categories for classifying marine heat waves for communicating to the general public. Prolonged and intense subsurface marine heat waves and their cumulative intensity result in increased thermal stress encountered by benthic organisms in depths down to 2,000 meters. So here you can see that there's the dashed line representing the temperature time series, where the thick black line representing the mean climatology, and the 90th percentile threshold limit is the line which defines the whether marine heat wave is present or not. So if the threshold is exceeded for more than 5 days, it's considered to be a marine heat wave event. And depending on the intensity of this threshold exceedance, we can categorize the marine heat waves as moderate, strong, severe, or extreme, or category 1, 2, 3, or 4. And so bottom marine heat waves can be more intense and persist for longer durations than surface marine heat waves when present. And possible impacts on biodiversity include large-scale mortality, species distribution shifts, and genetic tropicalization of temperate ecosystems. So, here is a map of the key global events of marine heat waves occurring since 1995. Studies have shown that there's a 10 times increase in intensity than pre-industrial levels, and a 50% increased frequency in the last 10 years. Also, the duration of marine heat wave events has also increased, affecting the cumulative intensity. The areas relevant to this study are circled in red. So that's the Blake Plateau, the Mediterranean, and cold water coral regions in the Northeast Atlantic. Also the duration of, you may be familiar with events such as the blob in the North Pacific in 2014, and you may be aware that the marine heat waves have led to the 4th global mass coral bleaching event this year for tropical corals. So there's a deep ocean knowledge gap on the impact of marine heat waves on cold water corals. So this study aims to better understand these impacts. A desktop modelling study utilising the GLORIES 12 version 1 product of the Copernicus marine marine reanalysis took place. So this is a global ocean eddy resolving reanalysis covering the altimetry from 1993 onwards, and it has 1/12 degrees horizontal resolution and 50 vertical levels. So 2 study sites were selected based on N members in the gradient of thermal tolerance, which is one of them is the southeastern United States Blake Plateau, Millions Mounds, which include Blake Plateau, and the region includes Million Mounds and Cape Lookout, where there's a strong influence of the Gulf Stream and associated oceanographic features such as warm core and cold core eddies. So corals are found to be resilient across a large temperature range here, whereas in the Mediterranean, which is future work, cold water corals are found to be living at 13 degrees or more, close to their upper limit of thermal tolerance. Corals here are thought to be least resilient due to the prolonged thermal stress. So the NOAA deep sea coral and sponge database was consulted, and the species occurrence data per hexapoint for stony branching corals was calculated for each hexagon in the grid in the study area. So, Desmophyllum producum are found to be between 4 degrees Celsius to 13.9 degrees Celsius, with the upper temperature limit of 15 degrees. Brooke et al. Suggested that there's a resilience to short-term temperature anomalies, such as short heat spikes, whereas cold water corals are less resistant to long-term temperature anomalies. Studies found that thermal tolerance with exposure to a wide range of temperatures in Cape Lookout in the North and Northwest Atlantic, where cold water corals experience temperature fluctuations of up to 9 degrees. Lophelia or Desmophyllum has lower energy reserves and skeleton growth than Madrepora, which has been found to be more resilient with increasing thermal stress. Most recently, Chemo et al. 2024 suggested the mortality in the long term at the holobiont level, as Desmophyllum can only tolerate increases of less than 3 degrees Celsius, resulting as a result of pathogenic bacteria. So preliminary hypotheses suggest that with the intensity and duration of subsurface marine heat waves predicted to rapidly increase in the next century, it will increase the thermal stress experienced by cold water corals and associated communities. So there will be increased stratification and increased mixed layer depth due to increased storminess and deepening of the thermocline. So cold water corals is likely to be affected physically. Cold water corals may be resilient to thermal stress physiologically, but the resulting physically dynamic environment will lead to secondary impacts on local scale in the benthic boundary layer. The mortality is more likely to be dependent on food availability and oxygen supply, whereas more severe consequences may be present for less frequent but more intense bottom marine heat waves. So in terms of physical oceanography and geology of cold water coral areas, there's the large-scale hydrography and local hydrodynamics affecting cold water coral growth and mound formation. Large-scale hydrography include the region include presence of the Antarctic intermediate water meeting at the Mound Province in the Gulf of Mexico. So temperature rise, flow preferences, and increased food availability. Internal waves have been found to be important for initiation of mound formation, as well as internal tides, which are related phenomena. Local hydrodynamics include the need to consider sediment dynamics in the benthic boundary layer, and the geology is very complex with glacial interglacial cycles of cold water coral mound development and the past geological record needs to be consulted. In terms of regional oceanography, there is the presence of warm core eddies and cold core eddies at Cape Lookout, causing temperature variability. So the questions considered by the study include are really important in terms of the impacts on the physical oceanography. So during marine heat waves, to what extent is there increased stratification and increased mixed layer depth and deepening of the thermocline? So there is a deep ocean knowledge gap that will downwelling increase or will upwelling increase in future in the cold water coral areas? And how will this affect bottom marine heat waves in cold water coral areas in future? So, and also, are bottom marine heat waves of greater intensity but less frequent than subsurface or surface marine heat waves? And what are the implications of this on cold water coral communities? And what is the secondary effects of marine heat waves which are there? So does oxygen supply has been found to increase with temperature? What are the implications of this? Oxygen saturation has been found to increase with temperature. So what are the implications of this for cold water corals? So the data were processed using the heatwave R package in R, using the bottom potential temperature layer of the NatCDF data from the GLORIES dataset. The hexagon grid was derived from the NatCDF file, and the R package calculates the climatology for each hexagon point, and then the bottom marine heat waves in the Atlantic, in the northwest Atlantic cold water provinces. The number of bottom marine heat waves between 1993 and 2021 at the hexagon centroids were extracted and calculated. Following this, the key bottom marine heat wave event, based on the cumulative intensity metric, was used to identify each hexagon in the coral areas. So here you can see a time series of the number of bottom marine heat waves for each point in the hexagon, for each hexagon, showing the key marine heat waves between 1993 and 2021. Results show that Blake Plateau cold-water corals have been exposed to up to 100 bottom marine heat waves during the time period analysed. Analysis is still in progress, and we can compare extensive range of time series statistics in relation to the spatial distribution of cold-water corals. So comparing this result to the previous studies on the oceanography show that the Antilles current may be involved in governing the distribution of cold-water corals in Blake Plateau, and other meandering features associated with the Gulf Stream are really important in the southeastern United States. Furthermore, previous studies reveal that the third dimension, depth, show that surface marine heat waves increase the depth of the thermocline, increasing the mixed layer depth, and affect stratification. It is unclear that Ekman pumping, which makes a significant contribution to increased vertical exchange of water masses, will increase or decrease. So to conclude, I wanted to highlight the significance of bottom marine heat waves to habitat mapping of cold-water corals. This study highlights the need for four-dimensional studies considering both the spatial and temporal changes in habitat mapping. The benthic boundary layer dynamics, as well as the regional oceanographic processes, are important to be considered in habitat mapping, and there's a need for long-term temperature tolerance in situ measurements on cold-water corals. Habitat suitability models must consider temperature variability over longer durations, so there's likely to be a difference between marine heat waves and snapshot marine heat spikes. Cumulative intensity is an important parameter to incorporate into marine heat waves, into habitat suitability models. And temperature variability also suggests that sponge aggregations are also sensitive to temperature variability. So previous studies suggest that temperature variability is also important in governing the distribution of sponge communities. So conclusions of the desktop study include that bottom marine heat waves increase thermal stress experienced by cold-water corals in the study area. There's a significant increase in frequency and cumulative intensity over time, and there's a need to consider the drivers of marine heat waves in the analysis which characterise marine heat waves. So there's likely to be an increase of mixed layer depth and stratification, and it's unclear whether downwelling or upwelling will increase, but it is likely to be important for subsurface and bottom marine heat waves. This is work still in progress, and I'm actively looking for future projects to do with the Mediterranean, Angola and the Northeast Atlantic. So there's you can find out more about my results on the Shiny app, where you can visualize the time series for each hexagon by selecting the hexagon ID, and please feel free to reach out for any questions you may have. Thank you so much for listening, and here are the references. Okay, thank you very much.